Hello everyone, good morning and welcome to RRS Live. My name is Brandon Lucas. I'm a junior in the Randall Research Scholars Program here at the University of Alabama, and I'm working in the Human Technology Interaction Lab under Dr. Chris Crawford in the Computer Science Department, where we're building an interface that utilizes brainwave data to help regulate anxiety and assist with learning outcomes in technology education. The Human Technology Interaction Lab has two primary focuses: brain-computer interaction, also known as BCI, and human-robot interaction. The project I am working on with Dr. Crawford focuses on the brain-computer interaction aspect, which investigates how data from the electrical signals from our brains can be utilized in our interaction with technology. A primary goal of the lab is to investigate the impact that systems that respond to a cognitive state has on the users and how this can be utilized to improve the ways that we interact with technology. So the dual goal of this project relates directly to the problem of technology education. We want to determine whether integrating neurofeedback into technology education activities will both increase education outcomes and decrease anxiety while learning. So we're going to focus on technology skills in this presentation due to a number of reasons. The first being that technology skills are becoming an increasingly important part of our lives at a rapid pace. So as depicted in the graph, the demand is outpacing most other occupations very quickly, yet not being met nearly quickly enough. From phones to laptops to household appliances, computing now influences arguably every aspect of society, and the impact is projected to only become stronger. In light of this, new and engaging methods of education should be sought to fill this gap. The barriers to entry in technology education, however, are still significant. So one of the common causes of frustration in learning tech skills such as computer science is difficult syntax, which is like the punctuation of a programming language, and concepts presented to the user straight from the very first program very often. The program to the right shows the famous Hello World beginners program written in Java, which simply prints the words Hello World to the screen. But there are many concepts being utilized here, such as object-oriented programming, that beginning students are told to just ignore. Another difficulty is the perceived lack of applicability of material beyond the classroom. Students often spend their spare time playing sports or listening to music or engaging in social media activities, and will find it difficult to see how writing code to solve math problems or print Hello World to the screen will directly relate meaningfully and personally to their own lives. So another culprit for learning difficulty is anxiety. Teenagers rank anxiety as the #1 major problem among people their age in the community they live in, becoming a growing cause for concern in terms of hindering students' learning ability. We hope to reduce anxiety and bolster learning outcomes specifically by incorporating music into our project. So music has been an increasingly popular method for engaging students in technology education. Researchers have been exploring ways that music can be used to introduce students to technology concepts in ways that are both engaging and meaningful to them. One popular tool for this has been EarSketch, which provides its own Python programming interface that simplifies the music creation process and has a corresponding social music sharing website. So the idea behind this is to make the learning process personally meaningful to the learner and encourage creative expression. Existing programs like this show the potential for music to aid in learning. In our current project, music creation will be partially controlled by the student directly and partially controlled by the student's EEG brainwaves. Again, the goal is to create a tool to improve learning outcomes and regulate anxiety by allowing students to create music that is modified by their own EEG data. But what is EEG? EEG stands for electroencephalogram, which involves sensors called electrodes measuring neuronal activity, commonly used to diagnose epilepsy and other brain disorders. There are a number of different wave types of EEG that are correlated with different mental states. Alpha waves, for example, show reflective or restful states, whereas beta waves tend to represent an active or busy mind. And it's been hypothesized that individuals that are very stressed or anxious tend to have an over-representation of beta waves in their EEG. So a student's own physiological data has the potential to make learning material more engaging by bringing abstract technological concepts into direct contact with personal physical characteristics. In this case, the student's own EEG data. Incorporating this allows us to design applications that are affected by and can raise users' awareness of their own mental state, such as anxious or calm. Since a student simply being made aware of their anxiety levels actually has the potential to decrease them and improve concept retention while learning, incorporating EEG data is beneficial in facilitating this awareness and achieving these outcomes. So we're using the commercial-grade Muse EEG headset, which is comfortable and easy to use and far friendlier than most typical EEG methods. Previously, our lab designed NeuroBlock, a web-based program to teach brain-computer interface and computer science concepts. This project only had the goal of teaching students programming and BCI concepts in an easy-to-use manner. Students build program logic using a simple and intuitive interface that allows characters to move around on the screen. Logic can be incorporated to make those characters move based on the student's own EEG data. NeuroBlock uses a block-based programming paradigm to allow students to drag and drop simple representative blocks that translate to code logic instead of having to actually write the code themselves. Once we took on the goal of improving learning outcomes and reducing anxiety, we decided to integrate a music software into NeuroBlock. Building and integrating that audio interface is my role in the lab. This will allow students to choose from a collection of instruments and modify certain parameters of the music creation process. The environment depicted is a prototype that currently enables multiple instruments to play at once. When this is incorporated into the NeuroBlock application, students will be able to control certain aspects of the music, such as the instruments and the timing of the notes. However, other aspects, such as the tempo or the specific notes being played, will be directly controlled by the student's EEG data. For example, a more anxious user may have a song with a higher tempo than a more relaxed one, which may cue the student into their own anxiety and what may be causing it. And this increased interactivity may also lead to better concept retention. So to go a bit deeper into how audio components are being integrated, we're using the Muse EEG programming interface, which is an open source online JavaScript library, to communicate with the headset and send the relevant EEG data. For a block-based programming environment, we're using Google's Blockly to create the front-end drag and drop blocks that allow students to create music. The popular music creation JavaScript library Tone.js controls all functionality related to the music timing, instruments, and notes. And finally, all of these will integrate into NeuroBlock to be utilized in one interface by the student. So the next steps for this project involves expanding on the prototype and integrating it in NeuroBlock. After that, we plan on creating surveys that will objectively assess a student's anxiety levels after interacting with our program to see if our program was successful in reducing anxiety. Additionally, we plan to test students on basic programming and computer science concepts to see if their performance in them has improved. Hopefully, these surveys will determine the success of the interface and allow us to obtain feedback and modify it as needed. And with that, I would like to take any questions you may have.
Have you guys looked into looking at things such as heart rate? Because like you can wear smartwatches as opposed to giant headsets to collect EEG data. So have you looked into that?
Yeah, so there have been a couple projects in the past, even though this is all very new, that have looked at incorporating other physiological data into technology education. One example is there was a recent article published that uses motion sensors for a softball player, and the softball player throws multiple pitches, right? And in the application, they take a video of themselves doing that, and in the application, they can rate whether a pitch was good or bad or curveball or whatever. And then it trains a machine learning model to determine, to basically say they can use the app to film them in real time, and it'll tell them whether the pitch was good or bad immediately. So in direct relation to the heart rate question, we haven't looked at that specifically, and really no one has yet because this is very new research, but we specifically thought brain-computer interfaces would be more interesting and engaging for a student to see that their own mind can directly control an application.
Have you guys had the opportunity to test NeuroBlock yet? And if so, was it successful?
Yes, so we've actually tested NeuroBlock in an experimental pilot study on undergraduates here at the University of Alabama. And basically what they did was they took a BCI self-efficacy test before and after the use of NeuroBlock. And what we found was that they had statistically significant improvements in their comfort and how comfortable they were with BCI applications.
Brandon, what's the current status of your audio interface integration?
Yeah, so currently we have the music prototype built out in Tone.js, and the reason we wanted to do that, and we actually did that in fairly higher detail than we actually expect the students to be able to use, because we wanted to see if we could get each component working simultaneously within the block-based programming environment that we're going to use in NeuroBlock. So the current state is just a prototype that can play multiple instruments at once, but it's fully customizable. So you can play whatever sequence of notes you want, each note at whatever note timing you want within a greater collection of note blocks that form a sequence. And so all of these components will be what we'll be using in NeuroBlock, either on the EEG-controlled side or the student-controlled side.
Very good.
Thank you.